I guess one thing I'll say is our final exam, it's scheduled, you can look up when it is. It's fairly early in the exam period, so it's not too early to start studying. And I'll just tell you right off the bat that the exam that you will be given will be created the following way. Online you can find, I think, 11 exams, final exams, so that's about 275 questions. The exam that you'll be given will basically be a sample of those 275 questions, 25 of them. So if you do all of those exams, work through them, understand the things that, the solutions are there, but they're of course just a single letter option. But if you should understand those solutions, why they're the correct solutions. There's even enough exams you can test yourself on them if you want. Then that's your best form of preparation for the final exam. There won't be any surprises. On the other hand, there is a lot of material there to study. Okay. So today I want to talk about independent events that come up when they're the natural follow-up to what we were talking about last class, which was conditional probability. And again, although there's a sort of interpretation for independent events, a sort of natural way that we think of them, always we have to remember the actual definition. And the definition of two events being independent, so remember, events are just sets of outcomes. They're independent if the probability, so A and B are independent if the probability of A and B both occurring is just the probability of A times the probability of B. That's just what it means to be, for two events to be independent. And what does this have to do with conditional probability? Well, if you remember when we talked about conditional probability, some of these things showed up in there. So if A and B are independent, then what can you tell me about the probability of A given B? Well, independence is supposed to mean that telling you that B happened doesn't really tell you anything about whether A happened. So let's just write down the definition. Probability of A given B is the probability of A and B divided by the probability of B. But if A and B are independent, then the probability of A and B is just the probability of A times the probability of B. But now we have probability of B on the top and the bottom. So that's just probability of A. So in the case where A and B are independent and there's an annoying condition, probability of B should be bigger than 0, otherwise this division doesn't make sense. In the case where they're independent, then the probability of A given B is exactly the same as the probability of A. So really, the fact that I tell you B occurred does not give you any information about whether or not A occurred. All right. So let's look at some examples. Well, I guess, and symmetrically, you can do exactly the same thing here and talk about the probability of B given A. Exact same computation will show that that's equal to the probability of B. Okay. So let's look at a couple of examples. Rolling 2 dice D1 and D2, maybe a red one and a blue one. So this is a sample space we've seen before. It looks like pairs like this, D1, D2, where D1 and D2 are each an integer 1, 2, 3, 4, 5, or 6. And the probability of any particular event is equal to 1 over the size of S. In this case, it's 1 over 36. And that's for any outcome, not event, outcome in S. Okay. So we roll 2 dice, a red one and a blue one, and we look at the red number and we look at the blue number. It's one we've seen lots. So let's look at some possible events and see if they're independent. So here's one event. We'll call it A0, and we'll write it as, these are the outcomes where D1 is equal to 4. Okay, so what does that look like in terms of this set of possible outcomes that have D1 equal to 4? Well, that's just this, right? 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, and 4, 6. And let's look at another possible event, which is D2 is equal to 6. So before I write that down, do you think that these two events are independent or not? So I roll 2 dice, and I tell you that the second one, the blue one, came up 6. Does that tell you anything about whether the first one, the red one, came up 4? Shouldn't really affect it, right? So intuitively, we think that these two events should be independent, but we need to check our intuition. So what is this set where D2 is equal to 6? Well, that's just this set. All right, and well, we want to know if these things are independent, so we need to know A intersect B. So what's in that set? There's only one thing in that set, and it is D1 is 4 and D2 is 6. So that's the only thing that's common to both of those two sets. All right, so now we can check. Probability of A0 intersect B0. This is a uniform probability space, so I only need to know the size of this set divided by the size of the sample space. And so that is, the size of this set is 1. There's only one thing in it. It's when you roll 4 with the red and 6 with the blue. So that's 1 out of 36. And the probability of A times the probability of B. Well, what's the probability of A? Well, that's the size of A divided by the size of S times, and this is the size of B divided by the size of S. Size of this is 6, and the size of this is 6. So this is 6 over 36 times 6 over 36, which is 1 over 6 times 1 over 6, which is 1 over 36. So we check the definition of independence. So the probability of A intersect B, we computed it here, it's 1 over 36. And the probability of A times the probability of B is also 1 over 36. So these things are independent. Okay. And that's what we expected because, absent some kind of quantum physics effect, rolling the blue dice should not have any effect on what came up on the red die. So the conclusion, A0 and B0 are independent. Oh. So any question about that? So the event, the red dice comes up 4, and the event, the blue die comes up 6. Those are independent events. One of them, somehow knowing that one of them occurred doesn't have any effect on whether or not the other one occurred. All right. Let's take another example. Let's say A, we'll stick with the same one. That's D1 is equal to 4. So we have a description of that set over there. I won't write it again. But B will be the event D1 plus D2 is equal to 7. So the event A depends only on the value of D1. The event B depends on the value of D1 and D2 that they somehow combine to give 7. Do you think that A and B are independent? Intuitively, I would, if I had to guess, I would say no, because B and A both depend on this value of D1. So somehow they're linked here. So that seems like they're not independent. But that's just intuition. What we actually need to do is just test whether or not they satisfy the definition of independent. So, the set B. So these are the pairs that add up to 7. So we've got a 1, 6, a 2, 5, a 3, 4, a 4, 3, a 5, 2, and a 6, 1. All right, so that's A and B. We need to know A intersect B. What's in both A and in B? Yep. 4. So everything in A has a 4 at its first position, and everything in B adds up to 7. So the only way that that works is if the second thing is a 3. Okay. So we have 4, 3, and 4, 3. That's the only thing that's common to those two sets. So now we can test things. The probability of A intersect B, the size of A intersect B over the size of S, which is what? One over 36 is the size of S. All right. Probability of A is what? So that's this guy up here. Size of A over size of S, 6 over 36, which is just 1 over 6. What about the probability of B? How many elements in B? 6 over 36. That's 1 out of 6. And so the probability of A times the probability of B is equal to 1 over 6 times 1 over 6 is 1 over 36. So are A and B independent? Yes. They satisfy the definition, right? Probability of A times the probability of B is equal to the probability of A and B. Okay. So again, you have to be careful with your intuition here. In this case, it led us astray. We said, well, A and B kind of depend on the same thing, so certainly they're not independent, but that's not what independence means. It doesn't mean that they don't depend on the same thing. It just means that one of them happening doesn't affect the probability of the other one happening. And sort of a nice way to see that or to think about that is just, you look at A and B, then A takes up, think of A taking up some fraction of the whole universe S. So it takes up some part of S, some fraction of the whole universe S, which you can think of as the probability of A. It's that fraction that A takes up. Now, if you look at A intersect B, then that A intersect B takes over some fraction of B. And if those two fractions are the same, then knowing whether or not B happened doesn't really tell you whether or not A happened. Okay? So, and that's exactly what's happening in this example. A was taking up 6/36 of S, which is just 1/6 of S, and A intersect B is taking up 1/6 of B. All right. So it looks like so far everything we've seen is independent. But let's just change it a little bit. Let's change this event to B prime. And instead of saying 7, let's say that these things have to add up to 6. Well, in that case, I have a 1 and a 5, 2 and a 4, a 3 and a 3, a 4 and a 2, a 5 and a 1, and I don't have anything over here. So if I just take the event B prime, which is that the sum of the two things is equal to 6, then I get a set of size 5 here. So the probability of A and B, well, what's A and B? In this case, 4 2 is the element in common. So A intersect B is 4, 2. So the probability of A and B is the size of A and B divided by the size of S, still 1 over 36. The probability of A is still 1 out of 6, but the probability of B is only 5 out of 36. And so when I take probability of A times the probability of B, I get 1 over 6 times 5 over 36. And what I can tell you is that that is not equal to 1 over 36. So the event A and the event B prime, so I should, of course, carry B primes through everywhere here. The event A and the event B prime, those are not independent. In fact, for dice, 7 is the magic number you can put here that somehow doesn't affect the distribution over the individual dice. So, questions about that? Yep.
Can you explain the diagram you made?
Sure, but it's just some little intuition. Just so, what is the probability of A? Right. So you have a set of possible outcomes, and you have a set A, and you can think of A as, or the probability of A as, how much of that set does A take up? In fact, in the uniform case, really it's just the size of A divided by the size of S. So it really is that ratio, right? How much of S is A taking up? That's the probability of A. Okay. Now when you bring a B into it, so remember, if these things are independent, that says the probability of A given B will actually just be the probability of A. So basically, so the first thing we were looking at was the probability of A this way. And the other thing that we can look at is A intersect B. And these things are, A and B are independent when these two things are equal. Okay. So that says, I tell you B happened, so now that's basically your whole universe. How much of that does A take up? How much of that universe does A take up? If it's the same as A takes up of this big universe, then that basically says A and B are independent. So I see the same fraction of things in B are A's as the fraction of things in S that are A's. Yep.
Can be the size of intersect A and B divided by the size of S?
Well, no. So this here is this conditional probability. This here is the probability of A given B, and so it's basically saying if they're independent, then the probability of A given B is just the probability of A, and this is what the probability of A is. So that's the conditional definition of independence. The sort of, not definition, but the implication that you get from here. The way to interpret it is, if I tell you B happened, I still don't know anything more about whether or not A happened. Yeah. Why isn't there a dependency? Or why is there?
They're not independent, right? Unless it's sum of B and B2 or something.
Yeah, well, for one thing, if I tell you that the sum is equal to 6, then I know neither D1 nor D2 is equal to 6. So already, certainly that's going to affect some probabilities about questions I can ask about D1, right? Like, what's the probability D1 is equal to 6, given that D1 plus D2 is equal to 6? The answer is 0.
Right, with 7 is every number.
With 7, every number appears for D1, and every number appears for D2. Exactly once, and in total 6 times, so you get the same ratio, 1 out of 6, basically. Okay. Good. Okay, here's a basic property of these things. So I think we're done rolling dice for a minute. In fact, I think I have, and when I've been talking in plain language, I've already been saying this without being really specific about it, but if A and B are independent, then A and the complement of B are independent. So in the sort of plain language thing, I've been sort of saying, well, if A and B are independent, then the probability of A doesn't change if I tell you B happened. It also doesn't change if I tell you B didn't happen. So in particular, knowing whether or not B happened does not tell you anything about the probability that A happened. So how do we prove this? So we have to show that the probability of A and not B is equal to the probability of A times the probability of not B. Okay? Now, we know, so that's the same thing as showing that the probability of A and not B is equal to the probability of A. And do we have another expression for the probability of not B?
1 minus.
Yeah. That's just 1 minus the probability of B, right? So either B happens or it doesn't happen, and it doesn't happen with probability 1 minus probability of B. Okay? So this is what we need to show, that the probability of A and not B is equal to the probability of A times 1 minus the probability of B. And A and not B are disjoint, right? Because everything in here is in B, and everything here is not in B. So there's nothing that's in both of those sets. And we also know, well, what's A? A, we can write it as you take everything in A that's in B, and you take everything in A that's not in B. Agreed? In terms of Venn diagrams, we have A, we have B. Some of the stuff here in A comes from B, and some of the stuff in A is not in B. That's all this says, right? Some of it's in B, some of it's not in B. And these are disjoint sets. So that means that the probability of A is equal to the probability of A and B, plus the probability of A and not B. All right? Now, if A and B are independent, that means this one we actually have a handle on. Right? If A and B are independent, that means that this is just the probability of A times the probability of B. That's the definition. Of independence. Okay, so now let's rewrite this. So on the left-hand side, I have probability of A. On the right-hand side, I have this product and this thing. So let's isolate A and not B. On the other side, we have probability of A. And then we got to subtract probability of A times probability of B. That's just rewriting this thing that has probability of A used to be on the left. We bring it over to the right. A intersect not B used to be on the right. We bring it over to the left. And this one we leave here. And everything gets negated. Now we're done because this is factor out probability of A, and you get 1 minus probability of B. So the probability of A intersect not B is equal to the probability of A times 1 minus the probability of B. And up here we said that's all we needed to show. And again, intuitively that makes sense. If telling you that B happened doesn't tell you anything about A, well then telling you that B didn't happen also shouldn't tell you anything about A. Okay. So questions thus far? All right. So there's this nice definition of independent here that tells you whether or not two events A and B are independent. It's sort of clean. It's easy to check and apply. And it seems to make intuitive sense to what we think it should mean for these things to be independent. Maybe the important thing to take away from this is that when A and B are independent, somehow, if you know that for some reason, someone tells you they're independent, then it's easy to compute their probabilities just by taking the product here. But what happens if we have more than two sets? So what does it mean to have or more than two events? What if we have like 10 events? What does it mean to say that those 10 events are independent? That we have to be a little more careful with. And in fact, there's more than one interpretation of that. So let's write down both possible interpretations and see some examples. So we'll say let A1 up to AN be a sequence of events. So different subsets of our probability space. Okay, then there's two definitions. A1 to AN are pairwise independent. if probability of AI and AJ is equal to the probability of AI times the probability of AJ, and that should be for all distinct pairs ij in the set 1 up to n. Okay? So I give you a bunch of different possible events, and I'll say that they're pairwise independent if I take any pair of those events, and those two events in that pair, they're independent. Because that's all this is. This says AI and AJ are independent, and the whole thing around this says that every single pair that we pick here should be independent. There's another definition of independence called mutual independence, which is much stronger. For every integer k, and I think you got to go from 2 up to n, and every I1 smaller than I2 smaller than I3 smaller than IK smaller, less than or equal to n, the probability of AI1 and AI2 and AI3 all the way up to AIK is equal to the product of their probabilities. Okay? So there's two definitions of independence for when I have a whole bunch of events. So pairwise independence says you take every pair of these things and you check to see if they're independent. If that's true for every pair, then the set or the sequence of events is called pairwise independent. And mutually independent is much more complicated. I have to take any subset of them with at least two elements in it and check that the probability that that subset of events all occurs is equal to the products of their individual probabilities of occurring. So a couple of things to note here. Both of these are awkward, but one of them is way more awkward than the other. So this thing here, here you need to check every pair. So that means you need to check and choose two things. Equations, I guess. That's for pairwise independence. Here, I basically have to take every subset of these events and check to see if they satisfy this particular thing. And that means I need to check the number of subsets of an n-element set is 2 to the n, but I'm not interested in the empty set, and I'm not interested in the subsets of size 1, but every other subset I have to check. So I have to check that they're pairwise independent. I have to check that they're 3-wise independent, that they're 4-wise independent, 5-wise independent, all the way up to n-wise independent. So for big values of n, this is obviously not easy to do. And even for this, I I mean, this is still a lot. N choose 2 still gets big pretty quickly in comparison to N, but sometimes this is doable. Usually, somehow this kind of mutual independence is buried in the problem statement somewhere. Okay? And so that's things like, I roll 50 dice, D1 through D50, and my events are of the form D1 is equal to something, and A1 is D1 is equal to something, A2 is D2 is equal to something, A3 is D3 is equal to something. Then, with a lot of work you can check this, or you can kind of buy that, yeah, those events, each one of them only depends on the value of one die, and they all depend on different die, and the die were supposed to be independent, so the events should all be mutually independent. So mutual independence is hardly ever something that you check from the definition. It usually comes in the problem statement. Okay, so let's just check an example for n equals 3. So here's an example, what we'll call a random bit string, B1, B2. So we interpret that to mean our set of outcomes. There's 4 of them. They could be B1 equals 0, B2 equals 0, B1 equals 0, B2 equals 1, B1 equals 1, B2 equals 0, or B1 and B2 are both equal to 1. And the probability of anything is 1 over 4. So there's 4 options and each one is equally likely. So look at that random bit string, and we have names for the 2 bits, B1, B2. Okay. So here's an event A. An event A is the event which, if we write it out as a set, that's 1, 0 and 1, 1. Right, so these are all the outcomes where the first bit is equal to 1, B2 is equal to 1, so that'll be my second possible event. Those look like 0, 1, and 1, 1. And C will be B1 is not equal to B2. So these are the outcomes where the 2 bits are different. So that's 0, 1 or 1, 0. Okay. So let's check if these things are, so this is 3 events, so that means there's 2 possible interpretations of what it means for these things to be independent or not. They can be pairwise independent, we can check that, and they can be mutually independent, and we'll check that. All right, for pairwise independent, we need to check the probability of A and B. We need to check the probability of B and C, and we need to check the probability of C and A. So we need to compute those things. and see that they're equal to what we expect. Let's start with the basics. So what's the probability of A? So the probability that I get one of these two outcomes. So the size of A over the size of S, 2 over 4 is a half. And, well, we can do the same thing for B and C, right? Each one of those is a set of size 2. So the probability that it occurs is 2 out of 4. So probability of B and the probability of C is equal to a half. All right. A and B. What's in that set that's both in A and in B? Yeah. Just one thing in there. 1, 1. So what's the probability that that happens? 1 out of 4. And that is equal to 1/2 times 1/2, which is equal to the probability of A times the probability of B. So A and B, these two events, they're independent, right? Their probability, the probability of A and B is 1/4, which is equal to the probability of A times the probability of B. All right, what about B and C? What's in there? Yeah. 0, 1 is in B, 0, 1 is in C, and the other things are different. So that's just the probability of 0, 1. There's only one element in there, so it happens with probability 1/4, which is 1/2 times 1/2. So B and C, probability of B and C is equal to the probability of B times the probability of C. Therefore, they're independent. Okay, so that's independent. And C and A, let's see. What's the intersection of C and A? Yep. 1, 0 is in C, 1, 0 is in A, and these two things are not in the other. Okay? So that is a single one element set. It's 1 over 4, which is equal to 1/2 times 1/2. So indeed, C and A are independent. So we have 3 events. That means that we have 3 choose 2 pairs of events. How much is 3 choose 2? 3. And we've just checked every pair. We've just checked for all 3 pairs. We've checked that they satisfy the definition of independence. So A, B, and C are pairwise independent. So what about mutually independent? What's left to check? So we've checked every pair. This definition says you only need to check for pairs or triples or whatever, 4 tuples, 5 tuples, and so on. In this case, we only have 3 events, so we've checked every pair. We need to check for the triples. There's only one of those. So there's 3 choose 3. It's just one of those. So we need to know the probability of A intersect B intersect C, probability of A and B and C. What's in there? What's common to A and B and C? Nothing. Right. So there's no element that occurs in A, B, and C. So that's the probability of the empty set, which is equal to 0. And that is not equal to 1/2 times 1/2 times 1/2. So we conclude that these events are not mutually independent because we found a subset of them. We computed the probability that everything in that subset occurs, and it was not equal to the probability, the product of the probabilities, that probability of A times the probability of B times the probability of C. So A, B, and C are not mutually independent. So you see this stuff can be kind of tricky, right? Sometimes they're pairwise independent, but not mutually independent. Of course, if they're mutually independent, they're definitely pairwise independent because part of checking mutual independence is checking every single pair. So that's fine. But this is a more stringent requirement, being mutually independent, and this one passes the first test, but not the second. Yep.
So is it the same way to say that A, B, and C are not mutually exclusive?
No, I wouldn't say exclusive. Don't bring exclusive in. It's not about being exclusive or not. In this case, the reason that it happens that this probability is not equal to the probability of A times the probability of B times the probability of C. It just so happens that in this example, A, B, and C have an empty common intersection. But there's other things that could happen that would break this, right? It's not always the case that you find some set whose probability is 0. It's just you find some set whose probability is different from the product of the probabilities. All right. So now it's time to do an exercise from the book. I need some better chocolate. So we have 3 students, and the students' names are Annie, Boris, and Charlie. They're writing an exam. That has one question. And the question is, what is 26 times 26? Okay. So we'll define the events A, B, and C as respectively Annie or Boris or Charlie gets the correct answer. It's only one question, there's only one correct answer, so, and the person marking it isn't interested in giving part marks, so either they get the answer right or they get the answer wrong. And I'll tell you, Annie was paying attention when she learned how to do long multiplication, and with a question like this, she is very good at them. She will answer them correctly 9 times out of 10. So she has probability 9 out of 10 of answering this question correctly. Boris, not surprisingly, also gets this thing correctly with probability 9 out of 10. But Charlie is not so good. He only can handle these 2-digit multiplications 6 times out of 10, with probability 6 out of 10. All right. So far, so good. And everything is independent here. Okay? So, in particular, probability of A, or A and B are independent. So imagine Boris and Annie, they go to different rooms, they work out the question completely independently. Each one gets their answer correct with probability 9 out of 10, but that's independent of the other one. And the same thing with Charlie and Boris and Charlie, and even, if you like, even all 3 of them. So everything is completely independent. So like I said, this mutual independence is usually in the problem statement, and that's the case here. So 2 questions. So a meta question here is, Charlie feels like if he can get, that seems like what he wants to do, right? So let's try 2 scenarios. Scenario 1, nobody cheats. What is the probability that at least 2 students get the correct answer? Okay. So, how would you tackle that? So what are the ways in which that can occur? So I don't know, let's say E is the event. At least 2 students get the correct answer. So sometimes it's actually helpful when you don't know what to do to just keep writing the question down somehow in more precise or longer ways. So the same question again, E is the event, at least 2 students get the correct answer. Now I ask you about, the question is, what's the probability of E? Well then, for that, when you see this kind of thing, we sort of have always proceeded by explicitly, or as explicitly as possible, writing out what this set E looks like. Okay? here's the way two students can get the correct answer. Maybe Annie and Boris get the correct answer. Each one gets the correct answer, right? That's two of them. So if that happens, then the event E has happened. Or maybe it was Boris and Charlie who got the correct answer. So if that happens, Boris and Charlie both get a correct answer, and at least two of them get a correct answer. Or maybe it was Charlie and Annie. Right? Do you agree that this is the event E here? Yeah.
If all three get a
So if we're trying to calculate the size of E, we'll have to deal with that. But, right, so the question is at least two students get the correct answer. And so, I mean, this is all the ways that can happen. And even if all of them get the correct answer, then, yeah, it shows up here, and it shows up here, and it shows up here. Right. So we're not looking at the size right now. We're just saying that the event E is the union of three sets. It's these three sets here. Okay? And to keep, but what you said is important. So we have all the outcomes that can happen, and some of them Annie gets the correct answer, some of them Boris gets the correct answer, and a smaller number of them Charlie gets the correct answer. And what we've just looked at, what we just wrote, is the set E that we're interested in. You can get it by taking the union of this, A and B, and B and C, and C and A. And that's where at least two students get the correct answer, right? There's no other place in here where at least two students get the correct answer. All right. Okay, so probability of E is equal to the probability of that thing. All right, so I'd like to break this up now into some, into a sum actually. So, is this true? So, either Annie and Boris, or Boris and Charlie, or Charlie and Annie. Is that true? So is this probability equal to that probability? Not quite. Because if we go back to the Venn diagram here, Annie and Boris is this pink thing. Boris and Charlie is this orange thing. And Annie and Charlie is this blue thing. So we've overcounted this common part where they all get the correct answer. So we have to correct for that. Is that correct? Yeah.
2 times that number?
Yeah. Not only did we double count in here, we actually triple counted. Right? We counted it, well, the orange time, the pink time, and the blue time. So to be correct, we only want to keep one of those counts, so we should subtract 2 of the others. So minus 2 times that. All right. And now, the problem statement has said that everything is independent, nobody cheats, so we know how to compute these probabilities. So A and B, that should be probability of A times the probability of B. B and C is the probability of B times the probability of C. C and A is the probability of C times the probability of A, minus 2 times. And again, now we need complete mutual independence for this to be true. This is the probability of A times the probability of B times the probability of C. Okay. And now we have all of the numbers. This is 9 over 10 squared plus this is 9 times Boris is 9 out of 10, Charlie is 6 out of 10. So that's 9 times 6 over 10 squared. Here we have Charlie and Annie, so that's 6 out of 10 times 9 out of 10. And then finally we have to subtract. Annie is 9 out of 10, Boris is 9 out of 10, Charlie is 6 out of 10. So that's 9 times 9 times 6 over 10 cubed, which is equal to 459 over 500, which is exactly equal to 0.918. Okay. So the probability that at least 2 of them get it right is 0.918. So nearly 92% of the time, at least 2 students will get it right in this scenario. All right. So, question about that? That's relatively clear. Good. Let's look at the second scenario. Charlie realizes he's not as good as Annie at math and has an opportunity to cheat. So Charlie is just going to copy Annie's answer. Scenario 2, Charlie copies Annie's answer. Annie and Boris have absolutely no reason to cheat. They have no reason to trust the other's work more than their own, so they don't look at each other's answers or do anything. And now you ask, what is the probability that at least 2 students get the correct answer? So when does it happen that at least 2 students get the correct answer? What has to happen?
Annie has to get the correct answer.
Annie has to get the correct answer? And or?
Then or Charlie.
What's that?
If Annie gets correct, then Charlie automatically gets
So if Annie gets the correct answer, then we get 2 students getting the correct answer. Or Annie and Boris. But it doesn't really seem to to matter, right? If Annie gets the correct answer, then good, 2 students get it. If Annie doesn't get the correct answer, 2 students get it wrong, and which means that 2 students don't get the correct answer. So I don't know, E prime is this event, and E prime we just decided is just Annie. Annie has to get the correct answer. It's all riding on her now. So the probability of E prime, just the probability of A, which is 9 out of 10, or if you like, 0.9, which is lower than this. So Boris did his selfish thing of trying to improve his result by copying someone else's. But ultimately, what this did is it screws up the grade distribution in a negative way. So, you know, the professor maybe thinks that the exam is successful if, you know, 2/3 of the students get it right. And what Boris just did is he made it less likely that this was a good exam. In fact, he made it, he really skewed it in a really bad way. 10% of the time, like 2 of them get it wrong, and it's all riding on Annie. So, yeah, yep. Yeah, he increased the probability of him getting the correct answer, but he also increased the probability of 2 students getting the wrong answer. And really, the 2 students getting the wrong answer is the complement of the one that we wanted. Yeah.
Would it have been better to copy if his initial probability was like a lot lower, 2 out of 10 or 3 out of 10?
I don't know. I have to work through that. My intuition is no matter how bad Boris is. If all you care about is the number of people who do well, then yeah, that's not clear. You need to work through the exercise to do that exercise with Boris's probability being 1 out of 10. All right. So we'll leave it there for today.